Find the settlement from consolidation in inches from the load. In this problem, a vertical load of 800 pounds per square foot is applied to a soil profile consisting of an 8-foot thick layer of clay, which is above a 4-foot thick layer of sand, which is above a 10-foot thick layer of clay. We've also been provided the various soil properties. In this problem, only the clay layers will settle from consolidation. Both clay layers we've been provided with the overconsolidation ratio, the recompression index, and the compression index, sometimes called the virgin compression index. Soil settlement can be plotted on a graph where the vertical axis is the void ratio and the horizontal axis is the log of the vertical effective stress. The pre-consolidation stress of the soil occurs where the curve changes slope. There is a graphical technique used to determine the pre-consolidation stress, but we'll skip that for now. If the soil is normally consolidated, the point on the curve would be here, with the recompression curve to the left of the point and the virgin compression curve to the right. Since we notice that both clay layers are overconsolidated, they would both begin on the recompression curve. The final vertical effective stress of the soil equals the initial vertical effective stress plus the load. If the final stress is less than the pre-consolidation stress, then the entire consolidation occurs along the recompression curve, which has a slope equal in magnitude to the recompression index. If this is the case, we would use the recompression index in the consolidation settlement equation. However, if the final stress exceeds the pre-consolidation stress, we'll end up evaluating part of the settlement along the recompression curve and part of the settlement along the virgin compression curve. When solving for this second settlement, we compute the two consolidation settlements separately and then add them together. Let's begin with the 8-foot thick layer of clay. The initial effective stress is equal to the effective unit weight times the depth. Since the groundwater table is deep, the effective unit weight equals 110 pounds per cubic foot. If we don't subdivide the layer, we'll set the depth equal to the middle of the layer so that D equals 4 feet. And our initial stress is 440 pounds per square feet. After adding in the load, our final stress equals 1,240 pounds per square feet. And our pre-consolidation stress is the initial stress times the overconsolidation ratio, or 1,320 pounds per square feet. Since the final stress is less than the pre-consolidation stress, the settlement at a depth of 4 feet is only along the recompression curve. For this problem, we'll assume this is true for the entire 8-foot thick layer of clay. So we substitute in our known values and find the settlement in the top clay layer equals 0.65 inches. Next, we'll evaluate the settlement in the 10-foot thick layer of clay. As before, we determine the vertical effective stress at the midpoint layer of the clay, where the depth into this 10-foot thick layer of clay will be evaluated where D equals 5 feet. The initial stress is 1,880 pounds per square foot. After adding the load, we calculate the final stress value to be 2,680 pounds per square feet. For this lower clay layer, the pre-consolidation stress calculates to 2,256 pounds per square feet. This means the final stress exceeds the pre-consolidation stress of the soil, which means the 10-foot thick layer of clay will calculate along the compression curve and the virgin compression curve. After substituting in all the required values, we calculate the consolidation settlement in this lower clay layer equals 0.21 inches along the recompression curve and 3.59 inches along the virgin compression curve, for a total of 3.80 inches of consolidation. After adding the settlement from both clay layers together, we find the total settlement is 4.45 inches. So we return to our possible solutions and find the answer is C.